We were just talking about the Smirnov transformation for sampling from random variables on the real line. And now we're going to take a look at an example of how to apply the Smirnov transformation, and we'll try sampling from an exponential random variable. So let's let x be an exponential random variable with parameter lambda. And then the PDF of x is little f of x, which is 0 when x is less than 0, and it's lambda times e to the minus lambda x when x is greater or equal to 0. And the CDF, capital F of x, it's not hard to prove by integrating the PDF from minus infinity to x, or, to a or whatever. So for x, f of x is also 0 when x is less than 0, and this time it's 1 minus e to the minus lambda x for x greater or equal to 0. So you can check that. That's just a little very easy calculus problem. And now we want to sort of invert this CDF in some sense to get the Smirnov transform. But strictly speaking, this is not invertible, right? Because there are more than one value that take the value 0, more than one x for which f of x is 0. So strictly speaking, it's not invertible. But let's draw the picture and think about what's going on here. Turns out that it's essentially invertible in the cases that we care about. So this, let's do it in green to be consistent here. F, this capital F, the CDF, it's 0 here. And then when x is 0, it's still, this is 1, so it's still 0. And then it jumps up, and as x is going to infinity, it's converging to 1. This is going to 0, so it's going to 1. This is f. And now we want to think about, so we said it was not invertible, and so what do we do? Well, in the generalized case, we had to think about this g function, this inf over all x's such that a was less than f of x. So let's write that down and see if we can figure out what that was. And remember, so this is we only need to consider it for the open interval from 0 to 1. So g, let's do that in blue. We need to figure out what this g of a function is. It's the inf over all real x's such that a is less or equal to f of x. And this is for a in the open interval from 0 to 1. So let's think about some such a. Say we have this is our a here, something between 0 and 1. And, well, this f, being a CDF, we know, of course, that it's always non-decreasing. It's monotone. And in fact, in this case, it's strictly monotone. So there's a unique value, x over here. There's some unique x for any a that goes to that a. So f is essentially invertible. It's invertible on the positive axis here. So what's this going to be? Let's figure out what this is going to be. So this equals question mark. Let's figure it out. Well, let's write down what f is. Let's set it equal to a, and we'll solve for what this x needs to be. So a is 1 minus e to the minus lambda x, and we'll solve for what a is for a given we'll solve for what x is for a given a to invert this guy. So we move this over, e to the minus lambda x equals 1 minus a, and then take logs, divide by minus 1 over lambda, and we get x equals minus 1 over lambda log 1 minus a. Okay, so this is the sort of inverse of f on this positive part of the real line. And so this infimum, the smallest x such that a is less or equal to f of x, Well, that's just going to be that point, that sort of generalized, this sort of generalized inverse thing here. So this will be, well, I guess it's right, because a is only between 0 and 1, and then we always have this. So this is just this guy. This is just minus 1 over lambda log 1 minus a. So we're hot on the trail now. Things are looking pretty good. We got our g of a function. And now what was the next step in the Smirnov transform? Back up here to the statement. So we had our CDF. We defined this g function. We figured out what that was. We got a very nice expression. And now we need to let u be uniform. And then we just evaluate g on that uniform random variable. So now let u be uniform. I think it's clear from here on out. And then g of u, in fact, let's write out what it is. G of u, which is minus 1 over lambda log 1 minus u, is distributed exponentially with parameter lambda. So if we wanted to generate exponentially distributed random variables with parameter lambda, and we could just go on our computer, and there are, the sort of standard random number generator routines generate uniform random numbers, and so we could sample a bunch of numbers from the uniform distribution on 0 to 1, and then just evaluate this function on those numbers, and we would get samples from that exponential distribution. And one thing to note, this formula can actually be simplified a little bit here, because if u is uniform, then 1 minus u is also uniform. So in fact, we also have this little slightly simpler version, which is that minus 1 over lambda log of u is also exponentially distributed. It's going to be a different random variable, but it will also have the same distribution. So this is just a very, very simple application of the Smirnov transform. And there are a few random variables for which the Smirnov transform is the desired, the most appropriate, the most sort of most efficient, easiest way to sample them. There are some others for which it's not so helpful. In particular, the Gaussian distribution, the normal distribution on the real line, is not amenable to the Smirnov transform, because getting a closed form expression for the inverse of its CDF does not seem to be possible. And so there's another method people use called the Box-Muller method. That's two people's names for sampling from a normal distribution. So so this is not universally applicable. So that's the Smirnov transform. And next, we're going to look at another way of sampling called rejection sampling, which can be used for some more complicated distributions. And it's a somewhat more general type of method for sampling.